Welcome to day 7 of Unit 8. This is our last topic for the year. So far we've been looking, we looked at graphs and we decided what the first and second derivative were going to be. We looked at equations and used the first and second derivative to figure out things. Now we're actually going to draw graphs of the first and second derivative. So again, the derivative is f prime or y prime or dy over dx, and f prime, because it only has one tick mark, is known as the first derivative. And topics we've talked about with f prime, the first derivative, it is the slope of the function at any point, slope of the tangent line. So there are local mins and maxes when f prime is equal to 0. Okay, that means if the original graph has a min or max, the f prime graph, it would be an x-intercept. If f is increasing, then f prime is positive above the x-axis. If the original graph is decreasing, then f prime is negative. That means it's below the x-axis. That's the first derivative. Second derivative, or double prime, is the slope of the slope, or what we'd say is going to be the concavity. Well, when we actually do the second derivative, we're going to look at f double prime being the slope of f prime. We're going to use the same rules we did before for f prime. Now we can relate it back to the original graph that when f double prime is 0, it's an inflection point, and if f prime is increasing, then f double prime is greater than 0. That means the original graph is concave up. If f prime is decreasing, that means f double prime is less than 0. That means the original graph is concave down. And we'll go through examples exactly what I mean, but we're going to relate each graph to each other one at a time. So I have 3 examples here. Each time I give you the equation for the example, I normally just give you a graph, but I want to relate something when I'm done with all this. And we're going to draw first the first derivative, or f prime, of each graph. The equation doesn't really matter, we're just looking at the graph. So f prime is really just the slope. So when I look at this graph, I see this slope for the very first one. This slope is always a positive number, and I know for this example it's positive 2. So it becomes just 2 the whole time. So the slope here becomes y values here. So since the slope is always 2, the y values are always 2. Now this next example, we have something's going on here. We have a slope here that is positive. We have a slope on this side which is negative, and right here at x equals 1, we have a slope here equal to 0. So I have to copy this down, and right here at x equals 1, on this graph, it becomes an x-intercept. Because like I said, the slopes on this graph become the y values on this graph. The slope is 0, this y value is 0. Now over here I need positive slope, that means I need positive y values. And then over here I need negative, so it better look something like this. Now I don't care about the shape so much. Actually, I'm going to erase that. Erase it all. That's 0. Like I said, I don't really care about the shape, just to make sure it is what it should be. If you notice here, these y values are positive, this y value is 0, these y values are negative. Slope on the first graph becomes the y values on the second graph. This last graph, I have a couple of them. I have a slope of 0 here, because it's a max. The slope is 0 here, because it's a min. And this slope here is positive. This slope here is negative. This slope here is positive. So I'm going to note my 2 slope of zeros. It looks like it's at negative a half. And positive 3. So I need to go positive, 0, negative, 0, positive. So positive, 0, negative, 0, positive. Again, the slopes on this graph become the y values on this graph. And this is exactly what I have. I have y values that are positive. I have a y value equal to 0, y values that are equal to negative, a y value equal to 0, a y value equals positive. That matches those slopes. So for example 1, f prime is just a horizontal line. For example 2, f prime, it looks like is a negative slope line. And for example 3, it looks like I have a parabola. Those were all the first derivative. Now, I'm going to do the second derivative. I'm just going to slide it up, and I'll show all three at one time. But technically, to go from the first derivative to the second derivative, I'm just taking slope again. So, the slopes here are going to be the y values here. Isn't the slope of this whole graph just equal to 0? So this is what the graph looks like. Over here on the second one, let me see, what color should I pick? I'll pick purple. This one, it looks like the slope is always negative. I don't care what it is. You want to call it negative 2, call it negative 2. You want to call it negative 1, call it negative 1. I don't care, as long as it's just negative. And it's always the same. Again, the slope here is the y values here. Now this last one we have to do a little bit of work, because when we look at this pink graph, it looks like this pink graph has a negative slope. Looks like it has a min value right around here, about 1.5. Let's say the slope here is 0, and then the right side has a positive slope. So at 1.5, again I have to make this an x-intercept, because the slope of 0 becomes a y-intercept. Again, slopes here, y values here. Now I have to go negative, 0, positive, so maybe I would do something like this. Negative, 0, positive. If you notice, this y value here is 0, these y values here are positive, these y values here are negative. And in fact, now we're going to connect everything together. Okay, if you look carefully at what we got, we have all three graphs here together. Let me see if we can pull this up. So looking at everything together, my original graph was 2x. When I do it the first time, the first derivative, f prime is the slope of the original graph, f of x. The slope of 2x is really just equal to 2. And then this f double prime is the slope of f prime of x. Well, if f prime is 2, the slope of that is equal to 0, and it works. I could also do the same thing over here. Let me pick green. When I go from the original graph to this, f prime is the slope, and the slope of this function is going to be negative 2x. That looks like negative 2x. And when I go from here to here, f double prime is the slope of f prime. Well, that is negative 2, and that does look like negative 2. But the big picture is this. When you want to go from the original graph to f double prime, from the original graph to f double prime is the concavity of the original function f of x. If you notice, this number is always negative. This value here is always negative. Y is always negative here, and that means the original graph was always concave down, and it is. Now the last graph over here, let's connect these two together. Remember, f double prime is the concavity of the original function f of x, and right here is y equals 0. This is the inflection point. So if I go, this is at x equals 1.5, I go to x equals 1.5 here, which is right around here. This is the inflection point. Okay, these positive y values means this part of the graph is concave up. And if I notice on this right side, from here to here, the graph is concave up. And since these y values are negative, that means this part of the graph has to be concave down, and it is concave down. So that's what we're looking at. So let's try a couple of derivatives of functions we haven't done yet. Let's try sine. So right here in blue is a graph of sine. Starts at 0, 0, goes up to 1, back to 0, down to -1, back to 0, and so on and so forth. It repeats. When I draw derivative graphs, I look for the zeros. I look for where the slope is zeros. So right here on all the mins and maxes, this is where the slope or the derivative is equal to 0. So these are these points right here. And notice it's going to be every other dot. And I look between what's going on. So this slope goes positive to negative to positive to negative to positive. So it looks like to me I should have positives to 0 to negative to 0 to positive to 0 to negative to 0 back to positive, and kind of repeats itself. And I say, wow, I've seen this graph before, and this graph is just cosine of x. So I think we just learned that the derivative of sine of x is cosine of x. Now I'm going to take the derivative of this graph, because it says this was f prime, and I'm going to take the next derivative of double prime. Again, all the mins and maxes become the x-intercepts on the next graph, because every place I put a purple dot, those slopes are 0. Looks like my slope goes negative, positive, negative, positive. So I need to go negative to 0 to positive to 0 to negative to 0 to positive to 0. And I say, this graph looks similar to the first graph. It goes to 0, 0, but it's kind of flipped upside down. So this is negative sine of x. Okay? So I think we just learned that derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. Well, if I go back to my unit circle, I know the positive x is a cosine graph, is cosine value. Positive y is sine. Negative x is negative cosine. Negative y is negative sine. And to me, this is the circle for derivative. The derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. Derivative of negative cosine is sine. So this is how I remember my derivatives for trig. Derivative of sine is cosine. Derivative of cosine is negative sine, and I just go around the circle. So, in summary, derivative of sine of x is equal to cosine of x. The derivative of cosine of x is equal to negative sine of x. I can write this correctly. So how about when I have these things in front called coefficients? Coefficients get a free ride. They just go along for the ride. So if derivative of sine of x is cosine of x, then 5 sine of x is going to be 5 cosine of x. Negative 2 cosine of x, well, the derivative of cosine of x is negative sine of x, times negative 2 is going to be positive sine of x. If I have, in general, ax, derivative of ax is going to be a cosine of x. And if I have a cosine of x, its derivative is going to be negative a sine of x. Okay, we're going to do one other function today, and that's e to the x. E to the x is the exponential growth. And if you don't remember, it starts here and grows. The general shape is something like this. So now I have to figure out what the derivative of this graph looks like. Well, let's see. the slope down here is getting closer and closer and closer to 0. If you look on the far left, farther left I go, I'm getting closer and closer to 0. And on the far right, this slope is going up and up and up to infinity. And maybe around here, if I had to estimate, this slope is about 1. So on the far left, I have to have a slope about 0. In the middle, I have to have a slope about 1. And on the far right, I have to have a slope that goes up to infinity. Well, I'm going to say this graph is going to look something like this. And I say to myself, those two graphs look familiar. Looks like the same graph as above. So what does it tell me? The derivative of e to the x is e to the x itself. Wow, that's really nice. And again, when I have coefficients, they get a free ride. If derivative of e to the x is e to the x, 1/2 e to the x is going to be 1/2 e to the x. -3 e to the x, its derivative is going to be -3 e to the x. If I have just a e to the x, it's going to be a e to the x. So today, we learned how to draw graphs of the first and second derivative, and we learned the derivative of sine and cosine, and the derivative of e to the x. So besides that power rule, which is very useful, you know some rules about derivatives. You can do some damage. Okay, last video of the year, last lesson of the year. Only one more thing to do, a couple quizzes and a test.